millions of people across Massachusetts, Rhode Island and Connecticut heard an explosion in the sky on Saturday afternoon. None of them saw what made it. NASA has now confirmed the source, a 3-foot meteor fragmenting at 40 miles altitude, 300 tons of TNT equivalent in energy released in a single second. But the agency's confirmation skipped the part of the case that actually demands explanation. Because at the exact moment the bolide exploded over Cape Cod, the entire sky above New England was covered by the cloud deck of a storm system that climatologically should not have been there at all. A late May nor'easter, moving south rather than north, sitting directly between the fireball and the ground. The result is one of the strangest evidentiary cases in recent atmospheric science. A confirmed atmospheric explosion across 3 states, with essentially no visual eyewitnesses, attributed entirely through a satellite designed for a different mission. If you want to understand what's actually going on, subscribe to the Sky Lab. We cover the stories behind the storms. Drop a comment telling me what you heard, where you were, and what you thought it was. Share this to help us grow this community. Let's get into it. Part 1. The Boom Heard. Across 3 states. At 6 minutes past 2 in the afternoon on Saturday, May 30th, 2026, something approximately the size of a small refrigerator hit Earth's atmosphere at roughly 20 times the speed of a rifle bullet, and the sky over New England disagreed with itself about what to do next. The first sign that something was wrong came in the form of a sound. People in eastern Massachusetts described it as a single, sharp boom. Some compared it to the closest, loudest crack of thunder they had ever heard, except there was no storm overhead to produce it. Others said it sounded more like a distant explosion, the kind you might expect to hear if a large industrial accident had occurred several miles away. A few people described it as a low, resonant pop that seemed to come from the sky itself, rather than from any direction on the ground. What everyone who reported it agreed on was that it shook things. Dishes rattled inside cabinets, picture frames moved against walls, windows vibrated, houses themselves seemed to shudder briefly, as if a heavy truck had passed too close, except no truck was anywhere near. The shaking lasted only a second or two. The sound lasted about as long, and then the afternoon was quiet again. Within minutes, the calls started coming in to local police departments across eastern Massachusetts. People wanted to know what had happened. They wanted to know if there had been an explosion somewhere. They wanted to know if a building had collapsed, if a gas main had ruptured, if there had been some kind of industrial accident at one of the regional refineries or chemical plants. They wanted to know if it was a sonic boom from military aircraft. They wanted to know if it was an earthquake. Across the entire eastern half of the state, in towns from Scituate to Cambridge, from Concord to Linfield, from Brighton to Wayland, the same question was being asked at the same time by people who had no idea their neighbours a few miles away were asking the same thing. The initial response from emergency services was understandable confusion. The Boston Police Department dispatched units to the Brighton neighbourhood on calls about a possible explosion. Other departments across the region fielded similar calls. None of them found anything. There was no smoke. There was no fire. There was no collapsed structure. There was no ruptured pipeline. There was no evidence on the ground of any event that could have produced the sound and the shaking that an entire region had just experienced. People started turning to the only other explanation that made sense in the absence of an obvious local cause. They started checking the United States Geological Survey website to see if there had been an earthquake. The USGS Did You Feel It system, which lets members of the public log reports of felt seismic activity, began receiving submissions from across eastern Massachusetts within minutes of the event. The reports described shaking that was consistent with what a small earthquake might produce. The intensity reported across multiple submissions clustered around what seismologists call modified Mercalli intensity level 4 or 5, which is the kind of shaking that rattles dishes and is felt indoors by most people but doesn't generally cause structural damage. The geographic distribution of the reports was consistent with an event whose source point was somewhere off the coast of northeastern Massachusetts. But there was a problem with the earthquake explanation, and it became clear very quickly. The seismic instruments that the USGS uses to detect actual earthquakes, the network of seismometers scattered across the northeast that pick up ground motion from genuine tectonic events, were not registering anything. There had been no detectable seismic source. The shaking that thousands of people had just felt across an entire state had not been caused by anything originating from inside the Earth. Whatever had happened, it hadn't happened underground. The National Weather Service forecast office at Mark's weather discussion page documented this transition explicitly in the public communication that started circulating that evening. The initial speculation, the office noted, had centered around the possibility of an earthquake, but the available seismic data had been unable to confirm any earthquake activity associated with the event. Attention, the office said, had since shifted toward a possible atmospheric source. The shaking had not come from below, it had come from above, and the only mechanism in the local atmosphere that could plausibly produce the kind of acoustic shockwave needed to rattle dishes across an entire state was an object moving through that atmosphere fast enough and large enough to generate one. You'll notice that this is already a different kind of mystery than most weather events the people of New England experience. A blizzard arrives with warning. A thunderstorm announces itself with thunder and rain. A tornado is preceded by a tornado watch, and then a tornado warning, and then sirens. Even a hurricane gives you a week to prepare. None of those events leave you in the position of standing in your kitchen, looking at the dishes that just rattled, asking yourself what could possibly have produced the noise you just heard. The May 30th event did exactly that to millions of people, and in the first hour after it happened, no one could tell them what had caused it. The geographic scale of the felt area was the part that compounded the confusion. If the source had been a single localized event in one town, the reports would have been concentrated near that town. They weren't. They came from across the entire eastern half of Massachusetts. They came from Rhode Island. They came from Connecticut. The Did You Feel It reports that came in over the following hours plotted out an area that stretched across roughly 12,000 square miles, encompassing 3 different states and an estimated population of several million people, all of whom had experienced the same boom and the same brief shaking at essentially the same time. A felt area that large is itself an interesting clue. Sonic booms from passing military aircraft, which do happen occasionally over the northeast, generally produce a much narrower felt corridor along the flight path of the aircraft. Earthquakes that produce a felt footprint that large generally involve at least a moderate magnitude tectonic event that would show up unambiguously on seismic instruments. The May 30th footprint was the kind of footprint you'd expect from a single, large, high-altitude event that generated a shock wave that propagated outward from a point source somewhere in the upper atmosphere over the region. And that found atmospheric conditions favourable to travelling unusually far before dissipating. But all of that was reasoning that emerged later. In the first hours after the event, the only thing that was clear was that something had happened to the sky over New England, that millions of people had heard it, that none of them had seen what produced it, and that none of the standard local explanations — building collapse, gas explosion, military overflight, earthquake — fit the available evidence. There was a boom, there was a brief shake, there was no smoke and no fire and no seismic signature, and no aircraft in the area that could account for what people had just experienced, and so the region settled into the strangest kind of public information limbo, where everyone agrees something happened and no one can yet say what it was. This is the situation that yesterday's video on this channel addressed. At the time we made that video, the case was still open. The Massachusetts boom was one of 2 unexplained sonic events on the East Coast in 48 hours. The other one had happened on May 28th over central South Carolina, and that case had its own set of strange features that we walk through in detail. We covered the South Carolina event extensively in yesterday's video. We laid out what NASA had said, what Shaw Air Force Base had said, what the National Guard fighter wing 30 kilometers away had not said. We walked through the hypotheses that were on the table for both events. We acknowledged that the South Carolina case was sitting in the federal record with no source attached, and we acknowledged that the Massachusetts case was still being investigated. What we said yesterday about the Massachusetts case specifically is that there was a strong satellite signature pointing toward a meteor entry. We said that meteorologists examining the satellite imagery had converged on a bolide interpretation within roughly 90 minutes of the event. We said that the American Meteor Society pending Fireball reports queue was receiving submissions from the region. We said that the most likely explanation, based on the available evidence at that time, was that something had entered Earth's atmosphere at high speed and had fragmented somewhere over the Cape Cod approach. And then, late yesterday afternoon and into the evening, the federal attribution arrived. NASA released a public statement on the event. The agency confirmed what the satellite data had been suggesting all along. The cause of the boom that had rattled dishes across Massachusetts, Rhode Island, and Connecticut on the afternoon of May 30th was a meteor. So the case is closed. The mystery has a resolution. The federal record now contains an attributed source for the Saturday afternoon event over New England. And under normal circumstances, that would be the end of the story. We'd run an update video that confirmed the attribution, walked through the technical details of what NASA actually said, and moved on to the next story in the news cycle. But that's not what we're doing today. Because the NASA confirmation, when you read it carefully, doesn't actually resolve the most interesting question the case raises. It resolves what made the noise. It does not resolve why no one saw the flash that should have accompanied a meteor of this size entering the atmosphere over one of the most densely populated coastlines in the country. It does not resolve why an event that under any normal set of atmospheric conditions would have generated thousands of visual fireball reports across multiple states, instead generated essentially zero confirmed visual reports. It does not resolve why the federal attribution chain had to lean entirely on a single weather satellite instrument to settle the case, and it does not resolve why that weather satellite was looking down at a patch of sky covered by a cloud deck that, climatologically speaking, should not have been there in the first place. Those are the questions today's video addresses, because what NASA confirmed is real. A meteor did explode over Massachusetts on Saturday afternoon. That part is not in dispute. What NASA left out, or what NASA didn't explicitly address, is the broader picture of what had to go right for the case to be solvable at all, and what that picture tells us about the population of similar events that don't get solved. Something doesn't add up about the way this case resolved, and the part that doesn't add up has nothing to do with the meteor itself. It has to do with the sky that was sitting between the meteor and the people who heard it. Let me show you what I mean. Because the part of this story that nobody in the standard news coverage is talking about is the weather that was happening above New England at the exact moment the bolide entered the atmosphere. And once you see what that weather was doing, the whole case starts looking very different. Part 2. The satellite that saw what no one else could. To understand why the May 30th case resolved the way it did, you need to understand a piece of federal weather infrastructure that most people have never heard of. It's called the Geostationary Lightning Mapper. It's a sensor that rides on board the GOES-19 weather satellite, which sits in geostationary orbit roughly 22,000 miles above the equator, looking down at North America from a fixed position in the sky. The instrument's primary job, the reason it exists, is to detect lightning. Not lightning the way you and I see it from the ground, with the bright flash followed by the rumble of thunder. Lightning the way the National Weather Service needs to see it, with hemispheric coverage, millisecond timing precision, and the ability to track storm development from above in near real time. What the Geostationary Lightning Mapper does, technically, is photograph the atmosphere of North America continuously at a rate of about 500 frames per second, looking specifically for flashes of light in a very narrow wavelength of the optical spectrum. The wavelength is 777.4 nanometers, which is the wavelength at which lightning is most optically brilliant. When the instrument sees a flash in that wavelength that fits the temporal and spatial signature of a lightning bolt, it records it. Over the course of any given hour, the instrument might record tens of thousands of lightning flashes across the continental United States, particularly during active thunderstorm seasons. The data feeds into operational forecasting products and into research on convective storm structure. It's an unglamorous piece of infrastructure that helps the National Weather Service do its job. But the Geostationary Lightning Mapper has a secondary capability that wasn't really the point of the design, but that emerges as a fortunate byproduct of its sensitivity. The instrument is so sensitive to brief flashes of optical light that it can detect non-lightning events that produce enough brilliance to register. The most important category of non-lightning events the instrument can detect is meteors. Specifically, very bright meteors, sometimes called fireballs or bolides, which are objects entering Earth's atmosphere at high speed and producing a luminous trail through their interaction with the air. When a meteor of sufficient brightness enters the atmosphere, the Geostationary Lightning Mapper sees it. Not the way an astronomical telescope would see it, with a continuous moving image of the streak. The mapper sees discrete flashes of light, picked up across multiple frames of its high-speed imaging, distributed along the trajectory of the bolide. From the satellite's perspective, looking down from 22,000 miles, a bright meteor entering the atmosphere over Massachusetts would appear as a series of bright spots, arranged in a narrow linear pattern that doesn't correspond to any thunderstorm activity. A meteorologist looking at the resulting data product would immediately recognize the difference between a thunderstorm signature, which clusters around a single point or follows the diffuse boundaries of a storm cell, and a bolide signature, which traces a straight line across an otherwise quiet patch of sky. That is exactly what happened on May 30th at approximately 10 minutes past 2 in the afternoon, Eastern Daylight Time. The geostationary lightning mapper, looking down at the New England coastline from its fixed position above the equator, registered a series of flash detections arranged in a tight linear pattern just north of Cape Cod. The detections were inconsistent with any active thunderstorm in the area. There was no thunderstorm in the area. The atmosphere over eastern Massachusetts that afternoon was occupied by a coastal cyclone, but not the kind of system that produces lightning. It was a cold, cyclonic, well-organized low-pressure system that was generating wind and overcast cloud cover, but no convective activity. The flash detections shouldn't have been there at all if you assumed they were lightning. They didn't fit the operational definition of lightning. They fit the operational definition of a meteor. A meteorologist on social media, posting under the handle Meteor Mark, that's Mark Margavage, who's been working as an operational meteorologist for years and has built up a substantial following by analysing satellite imagery in close to real time, caught the signature within hours of the event. He published the data product showing the linear flash detections plotted over the regional satellite imagery. The detections traced a path through the atmosphere that, when plotted alongside the geographic distribution of the acoustic eyewitness reports coming in from Massachusetts and Rhode Island and Connecticut, lined up exactly with what you'd expect to see if a bolide had fragmented at high altitude over the Cape Cod approach and generated a shock wave that propagated outward through the lower atmosphere from that point. The satellite signature and the ground reports were consistent with each other. They told the same story. They identified the same event. Within about 90 minutes of the boom, the convergence on bolide attribution had already started among the people who follow this kind of data closely. WBZ chief meteorologist Eric Fisher in Boston, who works in television but also takes the technical details seriously, posted his assessment that the available evidence pointed toward a meteor. Other operational meteorologists who had been watching the signature emerge throughout the afternoon agreed. By early evening, the geostationary lightning mapper data, the absence of any seismic signature, the geographic scale of the felt area, and the linear arrangement of the satellite-detected flashes had collectively produced a working hypothesis that was strong enough to publish. The American Meteor Society's role in all of this is worth a brief explanation because most people don't know it exists. The Society is a public organisation that maintains a website where members of the public can submit reports of fireballs they've seen. Anyone who witnesses a meteor entering the atmosphere can log onto the site, fill out a form describing what they saw, when they saw it, where they were when they saw it, and what direction they were looking. The Society aggregates these reports, plots them on a map, and uses them to triangulate the trajectory of the bolide. For events with substantial visual signatures over populated areas, the Society's pending fireball reports queue can receive hundreds of submissions within hours, and the resulting trajectory map becomes one of the primary data products used to characterize the event. For the May 30th Massachusetts event, the American Meteor Society's pending fireball reports queue began receiving submissions from the region within hours of the boom. The submissions were what filled in the picture from the ground side. People who had seen something, even just a brief flash through a cloud break, or a momentary brightening of the overcast as the bolide passed through, could log those observations. The Society's aggregated trajectory, the geostationary lightning mapper detections, and the geographic distribution of the acoustic eyewitness reports collectively told a consistent story about an object that had entered the atmosphere from the northeast, had fragmented at high altitude over the Cape Cod approach, and had produced a shock wave that propagated southward and westward through the lower atmosphere across the 3 states from which boom reports were coming in. By late Saturday evening, NASA had begun assembling the public statement that would arrive over the following 24 hours. The agency's process for this kind of attribution involves the NASA Marshall Space Flight Center in Huntsville, Alabama, which runs a meteoroid environment program that maintains models of the population of small objects in near-Earth space and characterizes the rate at which they enter the atmosphere. Marshall's role in a case like this is to take the available data, the geostationary lightning mapper signature, the eyewitness reports aggregated by the American Meteor Society, the geographic distribution of the felt area, and produce energy and parameter estimates that allow the agency to make a public attribution. That attribution arrived. NASA confirmed that the May 30th Massachusetts event was a meteor. The agency estimated the object's pre-atmospheric diameter at approximately 3 feet. The pre-atmospheric velocity was approximately 75,000 miles per hour. The energy released during fragmentation was approximately 300 tons of TNT equivalent. The fragmentation altitude was approximately 40 miles above ground level. The event was reported via the agency's official communication channels, and the federal record now contains a settled attribution for an event that, 24 hours earlier, had been one of the most discussed and least understood acoustic phenomena in the region's recent history. This is, in the strict procedural sense, exactly how the federal bolide attribution chain is supposed to work. A bright meteor enters the atmosphere. A federal sensor captures the signature. A public reporting organization aggregates the eyewitness data. A federal agency produces the energy estimate. The public attribution arrives within a couple of days. The case is closed. Except that we need to talk about how easily the chain almost didn't work in this specific case. Because the satellite that caught the meteor is not, in any meaningful sense, a meteor detection satellite. The geostationary lightning mapper is a lightning sensor. The fact that it picked up the bolide signature is a fortunate consequence of the instrument's optical sensitivity, not a deliberate design choice. There is no federal sensor system currently in operation whose primary mission is to detect meteor entries over the continental United States. There are research programs that look at the population of near-Earth objects in space. There are infrared sensor systems on military satellites that detect bright atmospheric events as part of missile warning operations, though that data is generally not released to the public. There are radar networks that catch some objects under specific conditions. But the operational, public-facing federal capability to detect a fireball entering the atmosphere over a populated area in real time is, in practical terms, an instrument that was designed to do something else. You can see why this matters. If the meteor had been slightly dimmer, the geostationary lightning mapper might not have registered the signature. If the entry geometry had been slightly different, if the fragmentation had occurred slightly farther offshore, slightly farther north, slightly farther beyond the instrument's most sensitive viewing angle, the satellite might not have caught it. If the May 30th event had happened over a part of the country less well covered by the instrument's footprint, or during a period when the duster product was temporarily down for maintenance, the case might never have been attributable from the available federal sensor data. The boom would have happened, the shaking would have been reported, the Did You Feel It system would have logged the felt area, and the federal record would have contained another unattributed acoustic event sitting in the catalogue with no source assigned and no resolution in sight. We know cases like this happen because they are in the catalogue. The May 28th South Carolina event we covered in yesterday's video is sitting in the federal record right now with the event type designation sonic boom and no source attached. NASA publicly stated there was no fireball detected. The conventional candidates, military, supersonic activity, seismic events, were ruled out by the relevant agencies. The case stayed open. And the only reason the May 30th Massachusetts case didn't end up in the same status is that the geostationary lightning mapper happened to be operating, happened to be looking at exactly the right patch of sky, and happened to register a signature bright enough to convert public ambiguity into federal attribution within 48 hours. What I want you to take away from this section is that the federal attribution chain for atmospheric bolide events depends on a much narrower set of capabilities than the public might assume. It depends, in practice, on a single satellite instrument that was built for a different purpose, plus a public reporting organization that aggregates eyewitness data, plus a federal agency that converts the resulting evidence into a public attribution. When the chain works, it works well. It worked on May 30th. The case resolved within 48 hours. But the chain is fragile, and the part of it that we'll get to in a few minutes is the part that mattered most on May 30th, which is what the ground-based component of the chain was doing during the event. Because the ground-based component, the visual eyewitness chain that under normal circumstances would have generated thousands of fireball reports from across 3 states, produced almost nothing on May 30th. And the reason it produced almost nothing is sitting in the satellite imagery that the geostationary lightning mapper was capturing at the same moment it was registering the meteor flashes. Before we get to that, though, we need to talk about the meteor itself in a little more detail, because the parameters NASA released are the kind of parameters that should make you stop and think about exactly what just happened over your country. Part 3. 300 tons of TNT over New England. Let me walk you through what NASA actually said the object was, because the parameters matter more than they might seem to at first glance. The agency's attribution describes a pre-atmospheric object roughly 3 feet in diameter, travelling at approximately 75,000 miles per hour, that fragmented at an altitude of about 40 miles above ground level, releasing approximately 300 tons of TNT equivalent in energy during the breakup. Each of those numbers is doing a specific kind of work in the attribution, and you can extract a lot of information from them about what was actually happening over New England that afternoon. 3 feet in diameter, that's about the size of a beach ball, a large beach ball or a small refrigerator, or roughly the dimensions of a household bathroom trash can. The object was not enormous. It was not the kind of body that would show up in the catalogue of catalogued near-Earth asteroids. It was at the very small end of the population of objects that hit Earth's atmosphere. Objects of this size are produced in large numbers by collisions in the asteroid belt and by the gradual fragmentation of comets that have passed through the inner solar system. They orbit the Sun in their billions. Most of them never come anywhere near Earth. Some small fraction of them eventually cross Earth's orbit. An even smaller fraction of those eventually intersect Earth itself. And so the population of small bolide events that happen on a planetary timescale is large enough that something of this size hits Earth's atmosphere on a weekly basis somewhere on the planet. Most of those events happen over the ocean, or over sparsely populated regions, or at hours when no one is paying attention. The May 30th event happened over a major population corridor on the United States East Coast during the afternoon on a holiday weekend. That's why we're talking about it. 75,000 miles per hour. That's the pre-atmospheric velocity. Let me put that in perspective. The fastest jet aircraft ever built, the SR-71 Blackbird, had a top speed of around 2,200 miles per hour. The May 30th bolide was moving more than 30 times faster than that. The International Space Station, which orbits Earth at about 17,000 miles per hour, was moving more than 4 times slower. The Space Shuttle on re-entry, which travelled at hypersonic speeds and produced one of the most famous re-entry phenomena in spaceflight history, was moving at about 17,000 miles per hour at the upper end of its re-entry profile. The May 30th bolide was moving more than 4 times faster than that. We're talking about a velocity that is so far outside everyday human experience that the only useful way to think about it is in terms of how the velocity converts into other physical quantities. Specifically, the velocity converts into energy. The kinetic energy of any moving object scales with the square of its velocity. Double the velocity and you quadruple the energy. Triple it and you increase the energy by a factor of 9. The May 30th bolide was moving at a velocity where its kinetic energy was enormous relative to its mass. A 3-foot rock at rest contains essentially no energy of interest. A 3-foot rock moving at 75,000 miles per hour contains an enormous amount of energy. The numbers NASA released give us the conversion, approximately 300 tons of TNT equivalent. That's the energy that was released into the atmosphere over New England when the object fragmented. 300 tons of TNT is, in absolute terms, a substantial amount of energy. It's roughly the energy released by a small tactical military weapon. It's about 3 times the energy of the explosion that destroyed the city block in Beirut Harbor in 2020. It's about 30 times the energy of the largest non-nuclear weapon currently in the United States military inventory. It's a quantity of energy that, if it had been deposited at ground level rather than at high altitude, would have produced a crater visible from orbit and a destruction radius measured in miles. But the energy wasn't deposited at ground level. It was deposited at 40 miles altitude in the upper atmosphere, where there are no human structures and where the energy dissipates through the thin air above the troposphere without producing any of the surface effects that would accompany a comparable energy release at the ground. This is the part that takes some getting used to. The May 30th event released more energy in a few seconds than most industrial accidents release in a lifetime, and it released that energy over the heads of millions of people. And the only thing the people on the ground experienced was a loud noise and a brief shake. There was no destruction, there was no fire, there was no debris that reached the surface, there was nothing for the news to show. The energy went into producing a shock wave that propagated through the lower atmosphere as a sonic boom. and into producing optical light that flashed briefly in the upper atmosphere before fading, and into producing some thermal heating of the surrounding air that quickly mixed out and disappeared. Everything else, the kinetic energy of the moving object, the gravitational potential energy of its altitude, the chemical structure of the meteoritic body itself, was converted in the space of a second or two into atmospheric phenomena that left almost no permanent trace. The fragmentation altitude of 40 miles is itself worth lingering on. 40 miles is well above the cruising altitude of commercial airliners, which fly at around 6 to 7 miles. It's well above the altitude where most weather happens, which is the lower 7 to 10 miles of the troposphere. It's right around the upper boundary of the stratosphere, in a region of the atmosphere that's sometimes called the mesosphere. The air at 40 miles is extremely thin. The pressure is something like 1/10,000th of sea level pressure. The temperature is cold but variable. There's essentially no water vapor. There's no cloud cover at that altitude because there's not enough air for clouds to form. The bolide that fragmented at that altitude was operating in an environment that bears almost no resemblance to the environment we experience at the surface. What fragmentation means at that altitude, mechanically, is that the object encountered air dense enough to produce decelerating forces, strong enough to overcome the structural strength of the body. As a meteoroid plunges into the atmosphere at 75,000 miles per hour, the air in front of it can't get out of the way fast enough to behave like a normal compressible gas. The air piles up at the leading face of the object and forms what's called a shock layer, a region of extremely compressed, extremely hot gas that exerts tremendous pressure on the front of the moving body. The shock layer is what produces the visible optical brilliance of the bolide. It's also what eventually destroys the object. As the body penetrates deeper into the atmosphere, the shock layer pressure increases. At some point, the pressure exceeds the structural strength of the meteoritic body. The body fractures. The fractured pieces are each individually exposed to the same shock layer pressure on their now smaller surface areas, which further accelerates the breakup process. Within fractions of a second, the entire body has been reduced to a cloud of small fragments, each one continuing to decelerate through the atmosphere and to radiate optical and thermal energy until it either reaches the surface as a small meteorite or dissipates completely. For a stony meteoroid of 3 feet in diameter, and we can be reasonably confident this was a stony body rather than a metallic one, because metallic bodies of this size generally penetrate to lower altitudes before fragmenting. The 40-mile fragmentation altitude is right in the expected range. The atmospheric dynamics produced exactly the kind of fragmentation event you'd predict if you started with the NASA parameters and ran them through the standard equations of bolide entry physics. The energy estimate of 300 tons of TNT is the integrated kinetic energy of the body, and its fragments as they decelerated through the atmosphere. The shockwave that millions of people heard was the acoustic signature of that deceleration event, propagating downward and outward through the lower atmosphere from the high-altitude source point. This is, in physical terms, an entirely well-characterized event. The numbers add up. The fragmentation altitude is consistent with the energy estimate, which is consistent with the diameter and velocity estimates, which are consistent with the eyewitness reports, which are consistent with the satellite signature. NASA's attribution is internally coherent. There is no reason, based on the physics, to doubt that the May 30th Massachusetts event was exactly what the agency says it was. A small stony meteoroid that hit the atmosphere at 75,000 miles per hour and broke apart at 40 miles altitude. Yesterday's video on this channel left 2 cases open, the South Carolina case from May 28th and the Massachusetts case from May 30th. Yesterday, both cases were in the federal record without attributed sources. Today, the Massachusetts case has a source attached: the geostationary lightning mapper signature, the NASA attribution, the American Meteor Society reporting chain, and the physical parameters self-consistency check all point to the same conclusion. The Massachusetts case is closed. That part of the open loop from yesterday has been resolved. The South Carolina case is a different matter. It remains in the federal record with the sonic boom event type designation and no source attached. We talked about that case in detail in yesterday's video, and we walked through the structural differences between the 2 events. We talked about NASA's on-the-record statement that no fireball was detected for the South Carolina event. We talked about Shaw Air Force Base's on-the-record statement ruling out conventional supersonic activity. We talked about the silence from the National Guard fighter wing 30 kilometers from the catalogued source point. None of that has changed. The Massachusetts attribution does not retroactively close the South Carolina case. The two events have different evidentiary profiles. One had a satellite signature that supported a clean attribution, the other did not. We're not relitigating the South Carolina case today. It has its own open question set, and that set remains open regardless of what NASA has confirmed about Massachusetts. What I want to focus on instead is the Massachusetts case as a case study in how the federal attribution chain works when the visual confirmation layer fails. Because the federal attribution chain succeeded on May 30th, but it succeeded through a much narrower path than the public typically realizes. The path it succeeded through is the satellite path. The path that should have been available, that under any reasonable set of atmospheric conditions over the Cape Cod approach on a Saturday afternoon would have been available, is the visual eyewitness path. Thousands of people should have seen the fireball, they didn't. And the reason they didn't is sitting in the same satellite imagery the geostationary lightning mapper was capturing when it caught the meteor flashes. It's time to talk about the sky over Massachusetts at 2:06 in the afternoon on May 30th. Because the sky was doing something it almost never does at that point on the calendar, and it was doing it directly between the bolide and the ground. Part 4. Why no one saw the fireball. Here's a question worth thinking about for a moment. If a meteor of the size NASA described, 3 feet across, travelling at 75,000 miles per hour, fragmenting at 40 miles altitude with 300 tons of TNT equivalent in energy released, enters the atmosphere over a populated area on a Saturday afternoon, how many people should see it? Under normal conditions, the answer is a lot. We're talking about an object that produces a visible streak across a substantial fraction of the sky. We're talking about a fragmentation event that under clear conditions appears from the ground as a bright flash followed by a slowly fading luminous trail, sometimes lasting for many seconds. We're talking about an event of sufficient optical brilliance to register on a satellite designed to detect lightning from 22,000 miles away. Anyone outside, with a view of the sky looking in roughly the right direction, would see something. People not outside but near windows would see something. Dash cams pointed at the sky would catch something. Doorbell cameras facing outward would catch something. Security cameras at gas stations and convenience stores and parking lots would catch something. The visual evidentiary record from a clear sky bolide event of this magnitude over the United States Northeast on a Saturday afternoon would typically run to hundreds of independent video recordings within 24 hours. The visual evidentiary record from the May 30th Massachusetts event is essentially empty. There are no widely shared dashcam videos of the bolide. There are no doorbell camera captures circulating on social media. There are no convenience store security clips. The American Meteor Society's pending fireball reports queue received submissions, but the submissions came from people reporting acoustic experiences and brief flashes through cloud breaks, not from people who saw the bolide itself in any detailed sense. The trajectory map the Society aggregated was constructed from a much thinner set of visual observations than a comparable event under clear skies would have produced. The bulk of the eyewitness data, the felt area, the boom reports, the shake reports, came in through acoustic channels, not visual ones. This is the structural anomaly of the case, and it's the part that the standard news coverage hasn't really addressed. Why didn't anyone see the bolide? The straightforward answer is that the entire region was covered in cloud at the moment of the entry. There was a cloud deck over eastern Massachusetts, over Cape Cod, over the immediately offshore waters of Massachusetts Bay and the Gulf of Maine, that prevented anyone on the ground from having a clear line of sight to the upper atmosphere. The bolide was fragmenting above the clouds. The shockwave it produced propagated through the clouds and reached the ground, which is why everyone heard it. The optical signature of the fragmentation, though, was happening on the wrong side of the cloud deck. From the ground, looking up, all anyone could see was the top of the cloud layer, lit slightly differently than usual for a moment, as the bolide passed overhead and then back to normal afternoon overcast. This is why the federal attribution chain had to rely entirely on satellite data to resolve the case. The geostationary lightning mapper was looking down from above the cloud layer. It had an unobstructed line of sight to the bolide. The cloud cover that obscured the event from millions of people on the ground was not in the satellite's way. From the satellite's perspective, the bolide was visible, the trajectory was clear, the flash detections lined up in a tight linear pattern, and the attribution was straightforward. From the ground's perspective, there was a sound from the sky and no source visible. Two completely different evidentiary pictures of the same event, separated only by the layer of clouds sitting between them. When you stop and think about what that means for the attribution process, you start to understand why this case is more interesting than the standard headlines make it out to be. The case was solvable because the satellite was looking. The satellite was looking because the geostationary lightning mapper happens to be looking continuously, regardless of whether there's a meteor or not. The satellite caught the signature because the meteor was bright enough to register through the instrument's optical detection threshold. The attribution was clean because the satellite signature, the eyewitness acoustic distribution, and the American Meteor Society reporting all fit together. Every link in that chain worked. The case resolved. But the chain almost didn't work. Pause for a second and consider the counterfactual. If the bolide had been slightly dimmer, the geostationary lightning mapper might not have caught it. The optical brilliance of a fragmenting meteoroid depends on multiple factors, including the body's composition, its entry angle, the fragmentation altitude, and the geometry of how the flash propagates through the upper atmosphere. The May 30th bolide was apparently bright enough, but it was probably close to the instrument's detection threshold for events of this size. A slightly less brilliant fragmentation event under the same conditions might have produced no satellite signature at all. The bolide would still have happened, the boom would still have been heard, the dishes would still have rattled, but the federal record would have shown an unattributed acoustic event with no source identifiable from available federal sensor data. We know cases like that exist, because the federal record contains them. The May 28th South Carolina event is one example. We're not going to relitigate that case today because yesterday's video already covered it in detail, and because its open question set is independent of the Massachusetts case. But the South Carolina case is sitting there in the catalogue, with the sonic boom event type designation and no source attached, because the available sensor data was not sufficient to produce a clean attribution. NASA stated no fireball was detected. The conventional candidates were ruled out by the relevant agencies. The case stayed open. It's still open. And the only reason it's open and the Massachusetts case is closed is that one of the two events had a geostationary lightning mapper signature and the other one didn't. This is the structural fact about the federal bolide attribution chain that I want you to really sit with for a minute. The chain depends, in operational terms, on a single weather satellite instrument that was built for a different purpose. When the instrument catches the signature, the chain works fast. When it doesn't catch the signature, there is no backup. There is no second federal sensor system whose primary mission is to detect bolides over the continental United States. There are research programs. There are military sensors that detect some events as part of other missions. There are infrasound stations that can pick up the acoustic signature of high-altitude explosions but whose data is generally not released to the public in real time. There are partnerships with the Comprehensive Nuclear Test Ban Treaty Organization that catalogue some events for nuclear monitoring purposes. But the operational, public-facing, fast turnaround attribution capability the United States deploys for events like the May 30th Massachusetts case is essentially the geostationary lightning mapper. What that means in practice is that the population of unattributed acoustic events in the federal catalogue is larger than the population of attributed events. Every case where the satellite layer fails, because the bolide was too dim, because the entry geometry was wrong, because the instrument was temporarily down, because the event happened in a part of the sky less well covered by the instrument's footprint, produces an unattributed entry. Those entries accumulate. They sit in the catalogue. They don't generate news coverage because there's nothing to report beyond loud noise heard, source unknown. Most of them get filed and forgotten. A few of them, like the South Carolina case from May 28th, generate enough public interest to warrant a video on a channel like this one, but most of them don't. What I want you to take from this section is that the May 30th case is not really a story about a meteor. It's a story about the conditions that have to align for a meteor event to be attributable at all. Those conditions aligned on May 30th. They could just as easily not have. And the part of the case that's most worth examining, and the part the standard news coverage has skipped entirely, is the layer of clouds that obscured the visual evidence chain and forced the entire attribution process to lean on a single satellite instrument. Because the cloud layer wasn't there by accident. The cloud layer was the product of a coastal cyclone that itself constitutes a meteorological anomaly. The atmosphere over Massachusetts at 2:06 in the afternoon on May 30th was doing something it almost never does at that point on the calendar. And the something it was doing was sitting directly between the bolide and the ground. When you put those two facts together, that a meteor happened to enter the atmosphere over a region where the entire visual confirmation chain had been eliminated by an anomalous storm system, and that the federal attribution chain succeeded only because a satellite designed for a different purpose happened to be looking, you get a different picture of what the May 30th case actually is. It's not the case where the system worked. It's the case where the system barely worked, on top of a meteorological anomaly that itself deserves an explanation. And that explanation is what we're going to spend the next part of the video walking through, because the storm that was sitting over Cape Cod at 2:06 on May 30th, 2026 was the weirdest storm to occupy that patch of sky in a very long time, and it's doing things that the climatology of the United States East Coast says it shouldn't be able to do at all. Part 5. A backwards nor'easter. In late May. The first thing to understand about the storm that was sitting over Cape Cod at the moment the bolide entered the atmosphere is that it shouldn't have been there. Not in the absolute sense. The atmosphere is capable of producing all kinds of configurations under the right conditions, and there's no climatological law preventing a coastal cyclone from forming off the New England coast at the end of May. But in the statistical sense, in the sense of what's normal for the calendar, in the sense of what a meteorologist would expect to see in the satellite imagery on May 30th, the system that was actually there was the kind of system you would not have predicted. A meteorologist named Mark Margovej, who posts under the handle Meteor on social media, flagged the storm in real time. He posted the satellite imagery showing the system at 5:26 in the afternoon Eastern Daylight Time on May 30th, several hours after the bolide had already entered the atmosphere over the cloud deck. The image showed a clearly organised coastal cyclone with a defined centre of circulation positioned off the New England coast. The cloud structure was textbook for a late-season nor'easter, a comma-shaped pattern of mid-level overcast wrapping around the low-pressure centre, with the densest concentration of cloud sitting directly over eastern Massachusetts and the immediately offshore waters. Margovej flagged two specific features of the imagery that he described as unusual. The first unusual feature was the calendar position. It was May 30th, and there was a nor'easter present. Nor'easters are a winter and early spring weather phenomenon. They form along the east coast of the United States when cold air from Canada interacts with relatively warm air over the Atlantic, producing intense low-pressure systems that ride the polar jet stream northward along the coastline. The climatological peak season for nor'easters runs from roughly November through April. By the end of May, the meridional temperature contrast that drives nor'easter formation has typically weakened to the point where these systems become rare. They do happen, but they're operationally unusual. A nor'easter on May 30th is not exactly a once-in-a-lifetime event, but it's roughly 2 to 3 weeks past the calendar window in which a system of this kind would be expected to develop. The second unusual feature was the direction of motion, and this is the part that makes the May 30th storm genuinely diagnostic of something larger going on in the atmosphere. Nor'easters, by definition, are extratropical cyclones that move northward up the east coast. The name itself comes from the northeasterly winds along the storm's northern and western flanks, which is what coastal residents experience when one of these systems passes. The climatology of the polar jet stream over North America keeps nor'easters tracking from south to north, riding the mean steering flow that has been the dominant feature of the Atlantic seaboard's weather for the entire instrumental record. A nor'easter moving north is the default behaviour of a nor'easter. It's what they do. The May 30th storm wasn't doing that. The satellite imagery Margovej published, and the operational forecasts coming out of the National Weather Service offices in Boston and Washington over the preceding 24 hours all showed the same anomalous feature. The storm's centre was tracking south rather than north. The system had spun up offshore on May 29th as a closed upper-level low detached from the main flow had reached peak intensity during the morning hours of May 30th, and had then begun drifting south and west through the day, rather than departing eastward into the North Atlantic, the way a typical nor'easter would. This is not a behaviour a nor'easter is supposed to exhibit. The only way you get a coastal cyclone moving in this direction is if the upper-level atmospheric configuration has been so radically disrupted that the steering flow has been displaced from its mean position, and a closed low has detached from the main flow into a quasi-stationary or retrograde regime. The National Weather Service Forecast Office in Washington characterized the storm's motion in their area forecast discussion as, and I'm quoting directly, slightly cut off as well as its slightly unusual retrograding track. The word retrograding is meteorology jargon for moving in the opposite direction from what the climatological mean would predict. The use of that word in an official NWS forecast discussion is the kind of detail that flags how unusual the system actually was. Operational meteorologists don't reach for the word retrograding lightly. It's the kind of language they use when they want to communicate that what they're looking at is not behaving the way the textbook says coastal cyclones should behave. The Boston Weather Service Forecast Office used similar language in describing the broader pattern. Their area forecast discussion characterized the storm system as, again quoting directly, highly amplified, meaning that the atmospheric wave pattern in which the storm was embedded had reached an unusually large amplitude relative to its climatological mean. A highly amplified pattern is one in which the polar jet stream has been pushed far south of its mean position over parts of the country and far north of its mean position over other parts, creating large bulges and troughs in the wave pattern that allow closed lows to detach from the main flow and become embedded in stationary or retrograde regimes. If you've been watching this channel for the past several weeks, that description should sound familiar. We've been talking about the highly amplified pattern over the United States continuously for the last 3 weeks. We covered it in our video from 3 days ago on the Omega block locking the atmosphere in place. We covered it in our video from 4 days ago on the drought break and what was replacing it. We covered the storm system that became the May 30th nor'easter in detail in our video from 2 days ago on the bomb-adjacent coastal cyclone heading for the East Coast. That earlier video walked through the Boston Forecast Office's characterization of the system in detail, the high wind warning for Cape Cod and Nantucket with 65 mile/hour gusts, the 5 storm warnings for marine zones from Maine to Long Island. The New York City Forecast Office's note that overnight lows at LaGuardia and JFK on Sunday morning would be within a few degrees of record lows for the calendar date, the snow flurry signal into the higher elevations of western New Hampshire, the late May Boston snow climatology backdrop pointing back to the last measurable May snow at Logan Airport in May of 1977 and the last measurable June snow in June of 1942. We're not going to rewalk all of that here. The point isn't to recap the storm itself. The point is to remind you that the storm sitting over Cape Cod at 2:06 in the afternoon on May 30th was not just any coastal cyclone, it was a specific anomaly with a documented set of features that the National Weather Service was actively flagging in real time. It was producing high wind conditions across the Massachusetts and Rhode Island coastlines. It was generating overcast cloud cover from Maine through Connecticut. It was producing temperatures 15 to 20 degrees Fahrenheit below normal for the calendar date across much of New England. It was a meteorologically anomalous event happening in a meteorologically anomalous direction, at a meteorologically anomalous time on the calendar, and it was sitting in exactly the right spot to obscure the bolide from the ground. You need to hold both of these facts in your head at once to understand what makes the case interesting. The bolide entry itself, the 3-foot rock at 75,000 miles per hour, was a statistically independent event whose timing was governed entirely by orbital mechanics, the Earth's position in its orbit, the asteroid belt's distribution of debris, the long-term gravitational interactions that determine which objects eventually cross our orbital path. None of that has any connection to what the troposphere over New England is doing. The bolide was going to hit the atmosphere when it hit the atmosphere, regardless of what kind of weather was happening at the surface. The cloud deck over Cape Cod, on the other hand, was the product of weather. Its timing was governed by atmospheric dynamics measured in hundreds of kilometers and hours, not by orbital mechanics measured in tens of millions of kilometers and years. The cloud deck was determined by the position of the closed upper level low, by the moisture transport from the western Atlantic, by the temperature contrast between the cold air aloft and the still moist boundary layer below, by all the conventional meteorological variables that produce the cloud cover associated with a coastal cyclone. The two events were independent in cause. They were coincident in space and time. The orbital geometry that brought a particular rock through Earth's atmosphere at 2:06 on May 30th had no causal connection to the atmospheric geometry that put a cloud deck over the entry point at the same moment. They both just happened in the same place at the same time for entirely different reasons. What I want you to focus on is what that coincidence does to the federal attribution chain. The federal attribution chain depends on multiple layers: satellite detection, eyewitness visual reports, eyewitness acoustic reports, infrasound monitoring, military sensor data, and so on. Some of those layers work in any weather. The geostationary lightning mapper works through clouds because it's looking down from above them. Eyewitness acoustic reports work through clouds because sound propagates through the lower atmosphere regardless of what's overhead. But eyewitness visual reports do not work through clouds. The entire visual chain, dashcam footage, doorbell camera captures, security camera recordings, eyewitness fireball descriptions, video clips posted to social media, depends on the existence of a clear line of sight between the bolide and the ground observer. On May 30th, that line of sight was eliminated by a cloud deck that itself constituted a meteorological anomaly. The attribution chain had to compensate by leaning more heavily than usual on the satellite layer. The satellite layer happened to be operating. The signature happened to be bright enough to register. The attribution went through, but the structural dependence of the case on a single sensor, a sensor designed for a different purpose, looking down from 22,000 miles away, catching a signal that was apparently close to its detection threshold for events of this size, is exactly the kind of dependence the public should know about, because the cloud deck wasn't an isolated event, it was part of a larger pattern, and the larger pattern is still in place, and there's no reason to think the next bolide entry over a populated area in the United States won't run into the same kind of cloud cover for the same kind of reason. When it does, the attribution chain will face exactly the same test, and there's no guarantee it'll pass. The storm that hid the May 30th fireball was not just a coincidence, it was a symptom of a larger atmospheric configuration that has been producing one anomaly after another over the United States for the past several weeks. That configuration is the part of the story we need to address next. Because the bolide and the cloud deck are both in different ways products of the same atmosphere. And that atmosphere is doing things right now that it should not climatologically be able to do. Part 6. What the storm was doing while the sky was falling. While the bolide was entering the atmosphere over Cape Cod at 2:06 in the afternoon on May 30th, the storm system that was sitting above it was doing other things too. The National Weather Service Forecast Office in Boston had issued a high wind warning for Barnstable and Nantucket counties. North winds were forecast to reach 25 to 35 miles per hour, with gusts up to 65 miles per hour. The warning was active from 8 in the morning through 8 in the evening on Saturday, May 30th, meaning that for the entire duration of the bolide's atmospheric entry, the same atmosphere was producing destructive wind conditions across the outer beaches of Massachusetts. If you've ever been on Cape Cod during a 65 mile per hour wind event, you know what that feels like. Trees come down, power lines snap, travel becomes difficult, especially for high-profile vehicles. Power outages spread across coastal towns. The Boston office's warning text said damaging winds would blow down trees and power lines, that power outages were possible, that travel would be difficult. This is the kind of language the National Weather Service uses for an event that has real human consequences. The marine impacts were more severe still. 5 separate storm warnings were active across the marine zones from Cape Elizabeth, Maine to Montauk, New York. Storm warnings, in the marine context, are issued for sustained winds of 48 to 63 miles per hour, second highest category, behind only hurricane force warnings. 5 of them simultaneously across roughly 600 miles of coastal waters on Memorial Day weekend is not the kind of thing that happens in late May under normal conditions. It's the kind of thing that happens during the active winter nor'easter season. The New York City Forecast Office's area forecast discussion noted that overnight low temperatures at LaGuardia and JFK on Sunday morning would be, in the office's exact words, within a few degrees of record lows for the calendar date. Sunday morning was the morning after the bolide entry. The overnight lows in question were the result of the same cold air outbreak that was producing the cloud cover over Cape Cod during the entry itself. Record-challenging cold overnight temperatures in the New York metropolitan area at the very end of May is, again, the kind of meteorological signal that flags an event running outside the normal climatological envelope for the calendar position. Frost advisories were active for interior southern New England. Snow flurries were forecast into the higher elevations of western New Hampshire. The Boston Forecast Office's discussion noted that the most recent measurable May snow at Logan Airport had occurred on May 9th, 1977. The most recent measurable June snow at Logan had occurred on June 11, 1942. The fact that operational meteorologists were having to reach back 4 to 5 decades to find calendar-relevant snow comparisons tells you something about how far outside the normal envelope the system was running. Now, hold all of that meteorological detail in your head for a moment and overlay it with what the bolide was doing in the same atmospheric column at the same moment. The bolide was fragmenting at 40 miles altitude. The fragmentation was producing optical brilliance, bright enough to register on a satellite from 22,000 miles away. The fragmentation was also producing an acoustic shockwave that would propagate downward through the lower atmosphere and reach the ground as a sonic boom. The boom would be heard across an area extending from Massachusetts into Rhode Island and Connecticut. Inside that same area, simultaneously, the high wind warning was active across Cape Cod and Nantucket. The storm warnings were active in the marine zones offshore, and the wind was already producing the kind of damaging conditions the National Weather Service had been forecasting for 24 hours. What this means in practice is that the public response to the bolide was happening inside a population whose attention was already partially occupied by the storm system overhead. Residents of Cape Cod and the south shore of Massachusetts were dealing with power outages and downed trees and travel disruptions when the boom hit. Residents of Boston and the inner suburbs were dealing with overcast skies and unseasonably cold temperatures when the boom hit. Residents of Rhode Island and Connecticut were dealing with the same cold air outbreak and the same overcast conditions when the boom hit. The atmospheric context in which the bolide entry was experienced by the public was not the context of a clear sky Saturday afternoon in late spring. It was the context of an active nor'easter, with all the meteorological signals that come with that kind of event. This matters for the visual confirmation question. People who are outdoors during a high wind event tend not to be looking up at the sky. They're focused on getting from one place to another safely, on keeping things from blowing away, on checking that branches are not about to come down on whatever they're standing under. People who are indoors during an overcast cold afternoon tend not to be looking out windows. They're focused on what they're doing inside. The behavioural pattern of a population during an active weather event is fundamentally different from the behavioural pattern of a population on a clear Saturday afternoon in late spring. Fewer people are outside. Fewer of those who are outside are looking up. Fewer dash cams are recording sky-facing footage, because the visibility conditions are poor and the operators are focused on the road. Fewer doorbell cameras are catching things because the people coming and going under the cameras are moving quickly, and the cameras themselves are pointed at ground level. Compound all of those behavioural factors with the cloud deck that was actually blocking the optical line of sight to the bolide, and the result is the visual evidentiary blank that the May 30th case left in the record. The conditions for visual confirmation were eliminated multiple times over. Cloud cover blocked the line of sight. The active weather event reduced the number of people in a position to look up. The overcast lighting conditions reduced the optical contrast between the bolide flash and the surrounding cloud deck. The cold temperatures kept people indoors. The result was that an event of substantial optical brilliance, occurring over one of the most densely populated coastlines in the country, on a holiday weekend, produced essentially no visual eyewitness record. The spatial overlap between the storm's felt area and the bolide's felt area is the part of this that you can actually plot on a map. The high wind warning area covered Barnstable and Nantucket counties on the Massachusetts coast. The bolide acoustic footprint covered the same counties, plus essentially all of eastern Massachusetts north and west of those, plus the Rhode Island coastline, plus eastern Connecticut. The two felt areas overlap almost exactly across the densest concentration of population in southern New England. The storm and the bolide were not just coincident in the abstract sense of happening on the same afternoon. They were spatially coincident in the specific sense of producing simultaneous impacts on the same population. If you were standing on a beach in Truro or Wellfleet or Provincetown on Saturday afternoon, looking out at the water with the wind whipping in your face at sustained 20 to 30 miles per hour, with the cold front having dropped temperatures into the low 50s and the cloud deck cutting off any view of the upper atmosphere, you would not have seen the bolide. You would have heard it. You might have felt the brief ground shake when the shockwave arrived, but you would not have been able to look up and see what made the sound. The storm was in the way. The cloud was in the way. The conditions of the atmosphere itself were in the way of the visual chain that should have produced your eyewitness report. This is what I mean by the storm being an active participant in the case. It's not just that there was bad weather on the day of a meteor event. It's that the bad weather specifically eliminated the public's ability to confirm the meteor through normal channels. The federal attribution chain had to compensate by leaning entirely on the satellite layer. The satellite layer worked. The case resolved. But the case resolved through a structural workaround that the public typically doesn't see, because the public typically doesn't have to think about the redundancy or non-redundancy of federal sensor systems for events that are usually attributed through the visual eyewitness chain instead. The question that the May 30th case forces on us, the question that NASA's attribution statement does not address, because the agency is in the business of explaining what happened to the meteor, not what happened to the visual confirmation chain, is what the federal record would have looked like if the satellite layer had failed too. We've already established that the satellite layer is one instrument, designed for a different purpose, with a detection threshold that the May 30th bolide apparently barely cleared. We've established that the visual chain was eliminated by the cloud cover from an anomalous storm system. We've established that the resulting attribution went through, but barely. The next question is what happens the next time, because the storm system that hid the May 30th bolide is not going away. Part 7. The Omega block is still holding. The reason the storm system was sitting over Cape Cod at the moment the bolide entered the atmosphere is that the United States atmosphere has been locked in a particular configuration for the past 3 weeks. The configuration is called an Omega block, named after the shape it traces on an upper-level weather chart, and we've covered it in detail in several recent videos on this channel. An Omega block is an atmospheric pattern in which a strong ridge of high pressure sits between two strong troughs of low pressure, with the whole structure standing essentially stationary over the same patch of geography for an extended period. Looked at from above, it traces the shape of the Greek letter omega, a high arch in the middle, flanked by deeper dips on either side. When one sets up over a continent, the steering flow that normally moves weather systems from west to east slows dramatically. Storm systems get stuck, heat waves persist, cold air outbreaks persist, drought and flooding both persist. The atmosphere stops moving the way it usually does. The current Omega block over North America set up 3 weeks ago. The ridge sits over the central United States. The western trough is over the Pacific Northwest, pulling cold maritime air down into California. The eastern trough is over the western Atlantic, producing the closed upper-level low that spun up the May 30th nor'easter and the overcast cold conditions that have been affecting New England for the past several days. We covered the western trough in detail in our video from a few days ago on the drought break, when the moisture surge driven by the configuration's southern flank was producing the first meaningful relief for the historic United States drought. We covered the persistence of the block in our video from 3 days ago on the continental flood forecast, when the same configuration was wringing out moisture over the northern Rockies on its way towards southeastern flooding. We covered the closed low on the eastern flank in our video from 2 days ago on the bomb-adjacent coastal cyclone, when the system that became the May 30th nor'easter was just starting to spin up off the New England coast. What I want you to take from those callbacks is that the configuration responsible for the May 30th cloud deck is not new news. It's been the dominant feature of our coverage for 3 weeks. It's been the dominant feature of operational forecasting for the same period. And it's not going away. The Climate Prediction Center's Day 8 through 14 Hazards Outlook, which is the federal product that addresses what the broader atmospheric configuration is expected to look like 1 to 2 weeks out, has the block holding through the first week of June. The cold side and the wet side of the configuration are forecast to extend into the early summer calendar. The same atmospheric architecture that produced the cloud deck over Cape Cod on May 30th is forecast to remain in place for at least another week, possibly longer. The Weather Prediction Center's medium-range discussion, which the agency issued at 3:54 in the morning Eastern Daylight Time on May 31st, describes the broader configuration as evolving toward a more zonal flow during the middle and late portions of next week. Zonal flow means wind flow that runs west to east along lines of latitude, which is what the atmosphere does under more typical conditions when there's no blocking pattern. The implication is that the block is forecast to begin breaking down over the course of the coming week, but slowly, and not before producing several more days of the kind of stationary weather pattern that has dominated the region for the past 3 weeks. Downstream ridging is forecast to spread above normal temperatures from the central United States into the east by the weekend, which represents a different kind of pattern transition rather than the kind of full release that would return the atmosphere to its climatological mean for early June. What this means for the question of bolide attribution under cloud cover is that the conditions that produce the May 30th concealment are not isolated. They're part of a larger pattern that has been persistent for 3 weeks and is forecast to continue for at least another week. During that period, the kind of meteorological setup that produced the May 30th cloud deck over Cape Cod will continue to be possible in similar configurations across other parts of the country. A bolide entering the atmosphere over an overcast region during the persistence of this pattern would face the same evidentiary problem the May 30th event faced. The visual confirmation chain would be eliminated. The federal attribution chain would have to depend on the satellite layer. The satellite layer would either work or it wouldn't, and the outcome of the case would depend on whether the bolide was bright enough to clear the detection threshold of an instrument designed for a different purpose. The storm prediction centers day. Two convective outlook for Monday, June 1st places a slight risk of severe thunderstorms across parts of the Central Plains. Large hail and severe wind gusts are expected as the pattern reorganizes and the next round of severe weather develops. This is the same atmospheric configuration that produced the May 30th cloud cover over New England. It's the same parent block that has been driving United States weather for the past 3 weeks. The severe weather setup and the cloud cover anomaly are products of the same atmospheric architecture. The block is still in place, the severe weather is still being produced on its margins, and the conditions that obscured the bolide on May 30th could be produced again in the coming days under the same configuration. I want to be careful not to overclaim. I'm not saying every bolide event over the next 2 weeks will be obscured by cloud cover, or that the Omega block is going to produce another nor'easter, or that the May 30th conditions will reproduce exactly. What I'm saying is that the population of cases where a bolide enters the atmosphere over a region of significant cloud cover, with the visual chain failing an attribution depending on the satellite layer, is going to keep growing as long as the block holds. Some will resolve cleanly through the satellite layer, the way May 30th did. Others will not, and they'll sit in the catalogue with the sonic boom event type designation and no resolution attached. This is the cumulative implication of the pattern's persistence. The May 30th case is one data point in a population of cases that the Omega block configuration is producing. The population includes attributed cases and unattributed cases. The attributed cases get news coverage, the unattributed cases don't, and the difference between attribution and non-attribution comes down to whether the satellite layer happens to catch the signature. Under the current pattern, with the cloud cover and the amplified atmospheric stratification both contributing to the conditions that make satellite attribution more important than usual, the ratio of attributed to unattributed cases is likely to shift in the direction of more unattributed cases sitting in the federal catalogue at the end of the month than would be the case under a more typical atmospheric configuration. The block is still holding. The cloud cover is still possible. The next bolide entry over a populated United States region is going to face exactly the same evidentiary test the May 30th event faced. Whether the test passes is going to depend on factors that have very little to do with the meteor itself and everything to do with what the atmosphere happens to be doing in that patch of sky at that moment. The case for which we have a clean attribution today is a case where everything happened to align. The cases for which we don't have a clean attribution, the ones that are going to happen over the next several weeks under the persistence of the pattern, are going to be cases where one or more of the alignments failed. The pattern is the reason the cloud cover existed. The pattern is the reason the visual chain failed. The pattern is the reason the attribution had to lean on a single satellite instrument. And the pattern is still in place. What the federal attribution chain looks like under continuous pressure from the same kind of conditions is the next thing we need to address. Because the chain that worked on May 30th is not a more robust chain than it appears, it's a less robust chain than the public assumes. And the reason it worked on May 30th has more to do with luck than with structural design. Let me show you exactly what I mean. Part 8. An instrument built for lightning caught a meteor. Let me tell you a little more about the satellite instrument that resolved the May 30th case, because the more you understand about how the geostationary lightning mapper actually works, the more clearly you see how thin the margin was between attribution and non-attribution. The instrument rides on board NOAA's GOES-19 geostationary weather satellite. Its official mission is to detect total lightning across the visible hemisphere from geostationary orbit at millisecond temporal resolution and roughly 8 km spatial resolution at the sub-satellite point. The physics is fairly simple. Lightning is an optical phenomenon as well as an electrical one. When a bolt discharges, the air around the channel is heated to tens of thousands of degrees Kelvin and radiates light across a broad spectrum, with particularly strong emissions centered at 777.4 nanometers, the spectral line of atomic oxygen. The mapper is essentially a high-speed camera looking at the visible hemisphere through a filter tuned to that wavelength. Software on the satellite processes the raw imagery into discrete flash events and downlinks them through NOAA's operational data feeds. The instrument was not designed to detect meteors. The fact that it can detect meteors is a fortunate side effect of its optical sensitivity. A bright bolide entering the atmosphere produces optical brilliance across a broad spectrum, including in the 777.4 nanometer band that the mapper is filtered for. If the brilliance is sufficient to exceed the instrument's detection threshold, the bolide registers. The geometry of detection is straightforward. The satellite looks down on the atmosphere, and any sufficiently bright event in its field of view produces a signal. And the temporal resolution of the instrument means that the trajectory of the bolide can be reconstructed from the sequence of flash detections, plotted in chronological order along the path of motion. The first time the geostationary lightning mapper attributed a bolide event as a public-facing federal action was in March of 2026, when a fireball entered the atmosphere over Lake Erie in northern Ohio. That event was captured by the GLM instrument on a previous GOES satellite. The Cooperative Institute for Meteorological Satellite Studies at the University of Wisconsin-Madison documented it in a public case study that's now one of the standard references for what GLM-based bolide attribution looks like as an operational process. The May 30th case fits the same pattern. The signature looked the same. The attribution chain followed the same steps. The case resolved the same way. What you should take from this is that the operational use of the GLM as a bolide attribution instrument is still relatively new. The first operational GLM launched in 2016. The use of its data for bolide attribution is a development of the last several years. The federal apparatus for converting GLM signatures into public bolide attributions is, in operational terms, a young system. It works when the signal is bright enough and the geometry is right. It's still being calibrated. The May 30th Massachusetts case was apparently a near-threshold catch. The instrument registered the signature clearly enough that the meteorologists examining the data could identify it as a probable bolide trajectory. But the signature was not the kind of overwhelming, unambiguous detection that would have made the attribution trivial. Mark Margavash's published analysis pointed out the linear arrangement of the flashes specifically because it was the arrangement that distinguished a bolide signature from a lightning signature, in a case where someone looking at the data without context might initially have assumed they were looking at lightning. The fact that operational meteorologists had to make a judgment call about what they were looking at, rather than having an obvious bolide flag immediately apparent in the data product, tells you something about the operational character of the detection. It worked, but it was not as automatic as the headlines might make it sound. The detection threshold question is the part I want you to focus on. Every sensor has a threshold below which signals don't register. For the GLM, the threshold for bolide detection depends on the optical brilliance of the fragmentation, which depends on factors like the body's composition, entry angle, fragmentation altitude, and the geometry of how the flash propagates relative to the satellite's line of sight. The detection probability for events of the May 30th energy class is, in practice, on the order of 50% to maybe 70% under reasonable conditions, with substantial uncertainty depending on the specific event. The events the GLM doesn't catch don't disappear. They go unattributed through the satellite path. They have to be attributed through other paths, visual eyewitness reports, infrasound monitoring, military sensors, or they stay unattributed in the federal record. The population of unattributed bolide-related acoustic events in the catalogue is, by direct implication, larger than the population of attributed events. The misses don't get news coverage, they sit in the catalogue. Yesterday's video addressed the May 28th South Carolina case as one example of a sonic boom event that didn't get attributed. That case has its own particular features that we walked through in detail, and we're not going to relitigate it here. But the structural point is the same. The South Carolina case is sitting in the federal record without a source. The available sensor data was not sufficient to produce an attribution. The case might or might not eventually be attributed if additional data becomes available. Right now, it isn't. And the South Carolina case is one example of a class of cases that the federal attribution chain produces whenever the satellite layer doesn't catch the signature, and the visual eyewitness chain doesn't produce sufficient evidence either. The May 30th Massachusetts case is a successful attribution. It's a case where the chain worked. The reason it worked is that the GLM caught the signature. The reason the GLM caught the signature is that the bolide was bright enough, the geometry was favourable enough, and the instrument was looking at the right patch of sky at the right moment. None of those factors are guaranteed for future events. The next bolide entry over the continental United States might be slightly dimmer, or at a slightly different geometry, or at a slightly different position in the sky relative to the satellite's coverage footprint, in which case the signature might not register and the case might not be attributable from available data. The public, when they hear about a meteor attribution like the May 30th case, naturally assumes that the federal system is designed to handle these events. The assumption is that there's a robust, well-funded, multi-layered detection apparatus that catches the population of bolide entries over United States territory and produces attributions in a routine and reliable way. The reality is closer to what I've just described. There is one operational instrument designed for a different purpose, with a detection threshold that catches most but not all of the events of interest, and a federal attribution process that converts the satellite signature into a public statement when the data is good enough. When the data is good enough, the system works. When it isn't, the case stays open. There is no second federal sensor system that would catch the cases the GLM misses. There are partnerships with other federal capabilities that contribute data in specific cases, but there is no equivalent of the GLM in the operational public-facing federal toolkit for bolide attribution over United States territory. What this implies for the public's mental model of how often these events happen is that the rate the public sees through the news cycle is lower than the rate that's actually occurring. The news cycle reports the cases that get attributed. The cases that don't get attributed don't generate news coverage, because there's nothing to report beyond loud noise heard, source unknown. Most of those cases get filed and forgotten by everyone except the people who were near enough to hear the boom and felt enough concern to log a report with the local emergency dispatcher or the National Weather Service field office. The federal record accumulates these entries quietly. The public's perception of bolide event frequency is calibrated against the attributed subset, not the full population. The real rate is higher than the apparent rate, and the difference between the two rates is exactly the population of cases the current federal attribution chain doesn't reach. This is the structural reality of the case the May 30th event illustrates. The attribution was successful, the system worked, but the system that worked is more fragile than the public typically realizes, and the population of cases the system doesn't reach is larger than the public typically realizes. The May 30th case is not the case where the system worked the way it always does. It's the case where the system worked in a specific instance, under specific conditions, with a specific set of factors aligned in its favor. The next case is going to be different. Some next cases will work the same way, other next cases won't. The federal record is going to keep accumulating entries on both sides of the line, and most of the public will never hear about the entries on the unattributed side because those entries don't make the news. What that means for the rate of these events and for what the population of cases actually looks like is the next thing we need to talk about. Part 9. How often does this go unseen? The question of how often events like the May 30th case actually happen has a fairly well-defined answer. NASA's Center for Near-Earth Object Studies, based at the Jet Propulsion Laboratory, maintains a public catalogue called the Fireball and Bolide Reports database, recording events detected by United States government sensors going back to 1988. For events in the 100 to 1,000 ton TNT equivalent range, where May 30th sits, the catalogue records dozens of entries per year globally. Most occur over the ocean or remote areas. The continental United States sees a small number of these per year, and only a fraction generate the kind of widespread public reports May 30th produced. The catalogue has a known limitation. It records only events detected by a federal sensor. Most entries come from the geostationary lightning mapper or from the infrasound network operated by the Comprehensive Nuclear Test Ban Treaty Organization. The catalogue represents the intersection of bolide events that occurred and detection events that registered on available sensors. The population that occurred without registering anywhere is not in the catalogue. How large is that uncatalogued population? The honest answer is that we don't know with precision. The cataloguing process improves over time as instrumentation improves, but there are always going to be events at the lower energy end that produce signatures too weak to detect, events in regions less well covered by the sensor network, events at unfavourable geometries that don't produce strong signals along the lines of sight available to operational sensors. Estimates from various researchers studying the population of small near-Earth objects suggest that the catalogue probably captures the majority of events above some energy threshold that varies over time and across sensor systems. For events in the May 30th energy class, the catch rate is probably reasonably good, meaning most events of this energy that occur over land in regions with good sensor coverage do get catalogued, but the catch rate is far from 100%. What that means for the May 30th case specifically is that you should think about the event as one realization of a distribution. The distribution describes the population of 300-ton TNT equivalent bolide events that occur over United States territory. Some of those events occur under clear skies, in regions with strong visual eyewitness coverage, where multiple independent confirmation chains produce overwhelming evidence within hours. Other events occur under conditions that eliminate the visual chain: overcast skies, nighttime entries over remote regions, unfavourable lighting, urban light pollution, and depend entirely on the satellite layer for attribution. Within that subset, some events have satellite signatures strong enough to register clearly and the attribution goes through. Others have signatures too weak to register, or geometries that don't favour satellite detection, and the events go unattributed. The May 30th case sits in the subset where the visual chain was eliminated and the satellite signature was bright enough to register. It's a successful attribution. The next case in the same subset might or might not be a successful attribution, depending on factors specific to that event. The case where the satellite signature is too weak to register is the case where the attribution fails. Those cases produce the same boom, the same shaking, the same public reports, and no resolution. They become entries in the federal record with the sonic boom event type designation, or some equivalent, and they sit there with no source attached, sometimes for years, sometimes indefinitely. The South Carolina case from May 28th might be one example of this class. Yesterday's video addressed that case in detail, and we walk through the particular features that distinguish it from a clear-cut bolide event. The point of bringing it up here is not to relitigate it, but to use it as an existence proof. The federal record contains cases where the available sensor data was not sufficient to produce attribution. The cases exist. They get catalogued with placeholder event type designations like sonic boom, magnitude 0.0, depth 0 kilometers. They sit there. Some of them are eventually attributed if additional data becomes available. Most of them just remain as catalogue entries with no source. What this implies for the public's understanding of how often these events occur is that the rate the public hears about through news coverage is lower than the actual rate. The actual rate includes all the cases where bolide events of this energy class occur, whether or not they get attributed. The reported rate includes only the attributed subset. The difference between the two rates is the population of cases the system doesn't reach. Most of those cases happen over the ocean, or over remote areas, where the boom isn't heard by anyone and the felt area is zero. Some of them happen over populated areas under conditions where the boom is heard but the source remains unknown. Those cases are the ones that occasionally generate public interest, and they're the ones that yesterday's video and today's video are addressing in different ways. The cumulative implication for the audience watching this video is that you should mentally adjust your expectation upward when you hear about a case like the May 30th event. The case is not an isolated curiosity. It's one realization of an ongoing process that produces events of similar energy class on a recurring basis. Most of those events you'll never hear about. A few of them, like May 30th, you will hear about because the combination of factors align to produce a public attribution and a news cycle. The cases you don't hear about are not less common. They're more common than the cases you do hear about. They just don't generate coverage because there's nothing to report. This is not a conspiracy. There's no entity actively concealing the rate of unattributed bolide events. The federal record is publicly accessible. CNEOS publishes its catalogue. The USGS publishes its earthquake catalogue, which includes the sonic boom event type entries. The American Meteor Society publishes its reports queue. Anyone with internet access in a couple of hours can verify the structural reality I'm describing. The reason the public doesn't typically know about it is that the data is dispersed across multiple federal databases, and the news cycle doesn't aggregate cases that don't have a clear public narrative attached. The information is there. The interpretive framework that organizes it isn't typically part of standard reporting. What the May 30th case provides is a teaching moment about the structure of the federal attribution chain. The case resolved. The bolide was real. NASA's attribution is sound. The public got an answer. But the case is best understood not as proof that the system always works, but as proof that the system worked this time, in this case, under conditions that happen to be favourable. The next case is going to be tested against the same set of factors. Some next cases will produce attributions. Others will produce catalogue entries with no source. The boundary between attribution and non-attribution sits exactly where the GLM detection threshold sits, plus whatever additional evidence the visual eyewitness chain happens to produce in each specific case. The May 30th case fell on the attribution side of that boundary. Other cases, including possibly the South Carolina case from 2 days earlier, fell on the non-attribution side. The chain doesn't fail catastrophically when it fails. It just leaves entries in the catalogue without sources attached, and the public doesn't usually notice. What this means for the immediate future is that the Omega block configuration that produced the May 30th concealment is still in place. The population of cases the configuration will produce over the next several weeks is going to test the federal attribution chain repeatedly. Some of those tests are going to pass, others are going to fail. The federal record at the end of the month will contain a few more catalogue entries on the unattributed side than would have been the case under a more typical atmospheric configuration. None of that will make the news. The public's perception of bolide event frequency will remain calibrated against the attributed subset. The actual frequency will continue to be higher than the apparent frequency, and the difference will continue to be hidden in the unattributed catalogue entries that don't generate coverage. That's the structural picture. The May 30th case is one data point in it. Now let's talk about the third part of why the May 30th case is interesting, beyond what NASA's attribution covers, the part that addresses why the boom was heard across 3 states when an event of this energy at this altitude would more typically produce a felt footprint of perhaps a single state or part of one. Because there's something about the atmospheric conditions on May 30th that may have widened the acoustic footprint substantially, and the mechanism that did so is, again, the same Omega block configuration that produced the cloud deck overhead. Part 10. The acoustic footprint question. The geographic distribution of the May 30th acoustic reports is one of the more interesting features of the case. Reports came in from across the entire eastern half of Massachusetts, from Rhode Island, from Connecticut. The total felt area, plotted on a map, extends across roughly 12,000 square miles. That's a substantial footprint for a single high-altitude atmospheric event. Under standard atmospheric conditions, a 300-ton TNT equivalent fragmentation at 40 miles altitude would be expected to produce audible reports over a roughly 50 to 100-mile radius from the ground projection of the fragmentation point. The May 30th reports extend well beyond that range in multiple directions, especially toward the southwest into Rhode Island and Connecticut. There are a few possible explanations. One is that the bolide's actual fragmentation energy was higher than NASA's estimate. Unlikely, NASA's number is probably accurate within a factor of 2, which isn't enough to explain the geographic extent of the reports. A second possibility is that the entry geometry produced an unusually directional radiation pattern, concentrating shockwave energy toward the south and west. Possible, but hard to constrain from available data. The third possibility, and the one I want to focus on, is that the atmospheric conditions over New England on May 30th were unusually favourable to long-range acoustic propagation. This possibility is consistent with the broader meteorological context that we've been walking through. The Boston Weather Service Forecast Office's area forecast discussion noted that the lower atmosphere on Saturday afternoon was characterized by lapse rates of 8 to 10 degrees Celsius per kilometre in the 1000 to 950 millibar layer. A lapse rate is the rate at which temperature decreases with altitude. 8 to 10 degrees Celsius per kilometre is a steep lapse rate. It's the kind of profile you get when the lower atmosphere is being aggressively mixed by strong vertical motions, which is consistent with the active cyclone overhead. A steep low-level lapse rate has implications for acoustic propagation. Sound waves travel faster through warm air than through cold air. When a shock wave generated at high altitude propagates downward into a region of strong vertical temperature contrast, the rays of the shock wave bend in response to the changing speed of sound across the temperature gradient. Under a standard atmospheric profile, the rays bend slightly upward, which causes the shock wave energy to dissipate into the upper atmosphere as it propagates outward from the source point. Under a steep lapse rate profile, the bending can become substantial. The rays can be deflected back toward the surface rather than dispersed upward. The result is what's called acoustic ducting, a phenomenon where shockwave energy is trapped in a layer of the atmosphere and propagates horizontally with much less dissipation than it would under normal conditions. The Boston office also noted an anomalously low altitude for the 925 to 850 millibar low-level jet, a narrow band of strong horizontal wind that typically sits a couple of kilometers above the surface. When the jet is at unusually low altitude, wind shear between the jet and the surface increases. The combination of steep lapse rate and anomalously low jet creates conditions favourable to acoustic ducting, trapping shockwave energy in a propagation channel that allows it to travel substantially farther horizontally than it would under a more typical profile. This is a speculative mechanism. I want to flag it clearly as speculation rather than as established fact. The atmospheric science of acoustic propagation under amplified pattern conditions is not as well understood as the atmospheric science of cyclogenesis or thermodynamic instability or any of the other better established branches of operational meteorology. There are research programs that look at this kind of question, but the operational tools for predicting how a shock wave from a high-altitude bolide will propagate through a specific atmospheric column on a specific day are not as developed as the tools for predicting where thunderstorms will form or how strong they'll be. The mechanism I'm describing is consistent with the conditions that were documented over New England on May 30th, and consistent with the unusually wide felt area reported by the public. But it's not the only possible explanation, and it should not be taken as the definitive answer to why the boom was heard so widely. What I want you to take from the speculation, with the speculation flagged appropriately, is that the same atmospheric configuration that produced the cloud deck obscuring the bolide may also have produced the acoustic conditions that made the boom audible across 3 states rather than just one. If that's right, then the Omega block configuration has had a dual effect on the public perception of the May 30th event. On one side, it eliminated the visual confirmation chain by putting a cloud deck between the bolide and the ground. On the other side, it widened the acoustic footprint by altering the atmospheric structure that governs sound propagation. The combination meant that more people heard the boom across a wider area than would normally be the case, and fewer people saw the flash than would normally be the case. The event became, in effect, more audibly impressive and less visually attributable than a comparable event under typical conditions would have been. That dual effect has consequences for the population of comparable events over the next several weeks while the pattern persists. If the same acoustic ducting mechanism is producing wider felt areas for high-altitude atmospheric events generally, then any bolide entries that occur under similar conditions are likely to generate more public reports across larger geographic regions than would be the case under a typical atmospheric configuration. Some of those events will get satellite attribution like the May 30th case. Others won't, and they'll produce public reports across regions large enough to attract attention, but with no clear federal explanation attached. The mismatch between the geographic scale of the reports and the resolution of the attribution will be a recurring feature of the cases that occur under the persistence of the block. There is a separate Storm Prediction Center concern for Monday, June 1st in the Central Plains, where a slight risk of severe thunderstorms is in place. The severe weather setup involves the same Omega block configuration that produced the cloud cover over New England. It's the same atmospheric architecture, just expressing itself through different surface-level manifestations in a different part of the country. Severe thunderstorms in Kansas and Missouri and Oklahoma on Monday afternoon are products of the same pattern that produced the nor'easter on Saturday. The configuration produces multiple kinds of weather simultaneously, and the cloud cover that obscured the May 30th bolide is one expression of that broader pattern. The severe weather setup in the Central Plains tomorrow is another expression. The combination tells you that the atmospheric configuration responsible for the cloud cover anomaly is the same configuration producing severe weather setups across the country, and the persistence of one implies the persistence of the other. What that means for the next case of a high-altitude atmospheric event over the United States, whether bolide, hypersonic vehicle re-entry, satellite breakup, or any other event that would generate an acoustic shockwave, is that the public response is going to be shaped by the same conditions that shaped the May 30th response: wider audible footprints, reduced visual confirmation, heavier reliance on the satellite attribution layer, more cases that resolve cleanly because the GLM caught the signature, more cases that don't resolve because something in the attribution chain didn't align. The cumulative effect over the coming weeks is going to be a federal record that contains more entries than usual, where the public response was substantial and the attribution was either successful through a single sensor path or unsuccessful through any available path. That's the broader picture the May 30th case is helping to illustrate. The case itself is now closed. NASA's attribution stands. The meteor was real. The energy estimate is consistent with the physical parameters. The federal apparatus did its job. But the case is also a teaching moment about how the federal apparatus does its job, and about how the public's perception of these events is shaped by the structural features of the attribution chain that the public doesn't typically see. The next case to come along is going to be tested against the same chain. The pattern is still in place. The cloud cover is still possible. The acoustic ducting is still possible. The boundary between attribution and non-attribution is still where it was on May 30th. And the federal record at the end of the month is going to contain whatever combination of attributed and unattributed cases the next several weeks produce. What all of this adds up to, when you step back and look at the May 30th case as a whole, is the next thing we need to talk about. Because the takeaway from this case is not the headline. It's not the meteor itself. It's not even the cloud cover that obscured it. It's what the case demonstrates about the relationship between the public's experience of these events and the structural reality of how those events get explained. Part 11. What the sky won't tell you. So here's what we know now that we didn't know 48 hours ago. A roughly 3-foot stony body travelling at approximately 75,000 miles per hour entered Earth's atmosphere over the United States northeast at around 2:06 in the afternoon on Saturday, May 30th, 2026. It fragmented at about 40 miles altitude, released approximately 300 tons of TNT equivalent in energy during breakup, and produced an acoustic shockwave that reached the ground as a sonic boom, audible across portions of Massachusetts, Rhode Island, and Connecticut. The boom rattled dishes, shook houses, and prompted thousands of people to log felt-shaking reports under the initial assumption that an earthquake had occurred. The assumption was wrong, because there was no earthquake. The actual source was a meteor, confirmed by NOAA's GOES 19 geostationary lightning mapper, looking down at the New England coastline from geostationary orbit, which registered a series of optical flashes in a linear arrangement consistent with a bolide trajectory north of Cape Cod. NASA confirmed the attribution and released the energy estimates. The federal record now contains a settled cause for the May 30th event. That's what NASA has confirmed. That's what the news cycle reported as the resolution. But here's what NASA's attribution didn't address, and what I want you to walk away from this video thinking about. The federal attribution chain that produced the resolution depended, in operational terms, on a single satellite instrument that was built for a different purpose. The instrument's bolide detection capability is a secondary affordance of its lightning detection mission, not a deliberately engineered design feature. The detection threshold for events of the May 30th energy class is in the range, where some events register and others don't, depending on factors like fragmentation altitude, optical brilliance, and entry geometry. The May 30th case happened to fall on the detectable side of that threshold. A modestly dimmer event under the same conditions might have produced no satellite signature at all, and the case would have stayed in the federal record without an attributed source. The visual eyewitness chain, which under standard conditions would have produced hundreds of independent confirmations from across the affected region, produced essentially nothing on May 30th. The reason is that the entire affected region was covered by the dense overcast of a coastal cyclone that was itself a meteorological anomaly. The cyclone was sitting in exactly the wrong position to obscure the bolide from the ground. The cyclone was tracking in exactly the wrong direction for the calendar position. The cyclone was producing exactly the wrong cloud structure for ground-based observation to succeed. The cyclone was the eastern flank of a broader atmospheric configuration that has been the dominant feature of United States weather for the past 3 weeks, and that is forecast to persist for at least another week. The combination of factors meant that the May 30th case was attributable through exactly one available path. Not 3 or 4 paths. One, the satellite path. If the satellite path had failed, and it could have easily under modestly different conditions, the case would have produced the same boom, the same shaking, the same federal database entries, and no source attached. It would have looked, in the federal record, like the May 28th South Carolina case that yesterday's video addressed in detail. That case is still sitting in the federal catalogue with the sonic boom event type designation and no source attached. The South Carolina case has its own particular features that distinguish it from a clean bolide event, and we're not relitigating it today, but the structural point about the South Carolina case is that it exists in the federal record as an unattributed entry. The federal record contains cases like this. The May 30th case almost became one of them. The reason it didn't become one of them is, in the most direct sense, luck. The GLM was operational, the geometry was favourable, the optical brilliance was high enough to clear the detection threshold, the signature was distinctive enough that operational meteorologists could identify it within hours. The American Meteor Society reporting chain aggregated the relevant eyewitness data. NASA's Marshall Space Flight Center converted the available evidence into a public statement. Every step of the chain worked, and the chain worked specifically because the conditions of the chain happened to align with each other in this specific case, on this specific afternoon, over this specific patch of sky. The next case might align differently. The next case might involve a dimmer bolide that doesn't register on the GLM. It might involve a bolide entering the atmosphere at a geometry less favourable to satellite detection. It might involve a bolide entering during a brief data outage of the GLM, or during a period when the instrument's coverage of the relevant patch of sky is degraded by other operational factors. It might involve a bolide entering during a period of overcast that extends across a larger geographic area than the May 30th event, or under different atmospheric conditions that change the propagation geometry of the optical flash. There are many ways for the chain to fail at the next case. There is no robust backup. What I want you to understand about this is that none of it is a conspiracy. There is no entity actively concealing the rate of unattributed atmospheric events. The federal data is publicly available. The CNEOS catalogue is publicly available. The USGS earthquake catalogue, which includes the sonic boom event type entries, is publicly available. The American Meteor Society pending fireball reports queue is publicly available. The Climate Prediction Center's Day 8 through 14 hazards outlook is publicly available. The Weather Prediction Center's medium-range discussion is publicly available. Any member of the public with internet access and a few hours can verify the structural reality I've been describing throughout this video. The reason the public doesn't typically know about this reality is that the data is dispersed across multiple databases, and the news cycle reports on attributed cases rather than on the structural conditions that produce attributions in some cases and not in others. What I also want you to understand is that the May 30th case is not exceptional. It's one realization of an ongoing process. The Omega block configuration that produced the cloud cover that obscured the bolide is going to continue producing similar conditions over the coming weeks. The storm prediction, Center's outlook for Monday, June 1st, places a slight risk of severe thunderstorms across the Central Plains as the same configuration produces its next round of surface weather. The Weather Prediction Center's medium-range discussion describes the broader pattern as transitioning more zonal mid to late next week, with downstream ridging spreading above normal temperatures from the central United States into the east by the weekend. The pattern is evolving, it's not breaking down completely. The conditions that produced the May 30th concealment are not going away. Over the next several weeks, the federal attribution chain is going to face the same kind of test that it faced on May 30th, possibly multiple times. Some of those tests will pass. The cases will be attributed cleanly through the satellite layer. The news cycle will report the resolutions. The public will get the answers. Other tests will fail. The cases will produce the same boom, the same shaking, the same public reports, and no resolution. They'll become catalogue entries with placeholder event type designations and no source attached. The news cycle won't report on them because there's nothing to report. The public will never hear about them. The federal record will accumulate them quietly on the unattributed side of the boundary between cases the chain reaches and cases the chain doesn't reach. This is the asymmetry I want you to leave the video thinking about. The May 30th case is the kind of case the public hears about. because it produced a clean attribution within 48 hours. The cases that don't produce clean attributions are the cases the public doesn't hear about. The rate the public sees through news coverage is calibrated to the attributed subset. The actual rate is higher. The difference between the two rates is sitting in the federal record, in catalogue entries that don't generate coverage, and the rate at which entries accumulate on the unattributed side is going to depend on how the omega block pattern evolves over the coming weeks. The longer the block holds, the more cases will face the May 30th test, and the more cases will fail it. The thing that's actually anomalous about the May 30th case is not the meteor. Meteors of this energy class hit Earth's atmosphere on a recurring basis. There's nothing exotic about a 3-foot stony body fragmenting at 40 miles altitude over a coastal area. What's anomalous is the convergence of factors that the case demonstrates. The cloud deck that obscured the visual chain was itself the product of an unprecedented late May coastal cyclone moving in an unprecedented direction. The acoustic footprint of the event was apparently widened by atmospheric stratification, produced by the same broader configuration that produced the cloud cover. The successful attribution through a satellite designed for a different purpose was the result of a fortunate alignment of factors. The South Carolina case from 2 days earlier, which faced a similar test and didn't pass it, is sitting in the federal record as a reminder that the alignment doesn't always hold. The persistence of the pattern means the next test is coming, possibly within days. The federal apparatus is going to do its best. The next case might resolve cleanly. The next case might not. What you do with this information is up to you. You can take it as reassurance that the system works. The system did work on May 30th. The case resolved within 48 hours. The bolide is now in the federal record with all the appropriate parameters attached. The visual chain failed, but the satellite chain succeeded. The atmospheric anomaly that obscured the event was itself a documented anomaly, with a clear synoptic explanation grounded in well-understood physics. There is no need to invoke anything exotic to explain the May 30th case. Everything that happened can be accounted for by standard atmospheric science and standard bolide entry physics. The case is, in the strict procedural sense, settled, or you can take it as a warning that the system is more fragile than the public typically assumes. The next case might not be as lucky. The federal record is going to accumulate entries that don't resolve. The public won't hear about them. The actual rate of these events will continue to be higher than the apparent rate. Both readings are defensible. The system did work on May 30th. The chain is fragile. Both are true at once. Which reading you find more compelling depends on whether you're more focused on the successful attribution that happened or on the structural features that made the attribution possible. The standard news coverage emphasizes the attribution. This video has emphasized the structural features because they're the part the news doesn't reach, and because they have implications for how to think about the cases coming over the next several weeks. So let me close with where the case actually leaves us. Millions of people heard a substantial atmospheric explosion across 3 states on Saturday afternoon. None of them saw what made the noise. The only reason there is an explanation in the federal record today is that a satellite designed for lightning detection happened to be looking down at the right patch of sky at the right moment, and happened to register an optical flash bright enough to clear its detection threshold. The same satellite that caught the meteor was looking at a cloud deck that should not have been there in the first place, produced by a storm system that should not have been moving in the direction it was moving on the calendar position it was at. The same atmospheric configuration that produced the cloud cover may also have widened the acoustic footprint to 3 states rather than just 1. The configuration is still in place. The pattern is forecast to persist for at least another week. The next case is coming, and the question of whether the next case will resolve like May 30th did, or whether it will fail to resolve and become another unattributed entry in the federal catalogue, is going to depend on the same set of factors that aligned in this case, and that might or might not align in the next one. That's the takeaway. The federal attribution chain is more fragile than the headlines suggest. The population of unattributed cases is larger than the published catalogue. The omega block configuration is producing conditions that test the chain more heavily than usual, and the public's perception of how often these events happen is calibrated against the attributed subset rather than against the actual population. The May 30th case is real. The meteor is real. The attribution is sound. But the case is also a teaching moment about the conditions under which the federal system delivers public attributions and about the conditions under which it doesn't. The sky over New England on Saturday afternoon was doing 2 things at once. One was concealing a meteor entry from the eyes of millions of people. The other was forcing the federal attribution chain to lean entirely on a single satellite instrument to settle the case. Both were products of the same atmosphere. That atmosphere is still up there. The pattern is still locked in. The next time you hear a loud noise from the sky, and the news cycle quickly tells you what made it, remember the May 30th case. The answer arrived because the conditions aligned. When the conditions don't align, the answer doesn't arrive, and the federal record fills up with catalogue entries that look exactly like cases where something happened, where millions of people felt it, and where the system that's supposed to explain it ran out of evidence to work with. That's the part of the case the headlines don't cover. That's the part that doesn't add up about how the May 30th case actually got resolved. The sky is bigger than the satellite that watches it. The atmosphere is more complicated than the chain that tries to attribute its events. The population of things that happen up there, that you and I will never know about, is bigger than the population of things we read about in the news. The next case is coming. Whether it resolves like May 30th did is going to depend on whether the satellite is looking at the right patch of sky at the right moment, catching a signature that's been built into the federal infrastructure as a fortunate side effect of an instrument designed to watch lightning. That's what the sky won't tell you. That's the part that doesn't add up. And that's what you should be thinking about the next time the boom you can't explain shows up in your dishes, and the news takes its time figuring out what made it.